welcome to my classroom. Today we will discuss soil properties in relation to soil erosion. In fact, if I say that this is a particular rainstorm A falling on soil A, and this is particular storm B, this is again falling on soil A, plus it is also falling on soil B. Now the rain, this rain has certain capability to cause erosion. We have discussed this last time and we call this as erosivity. Now erosivity of storm A is higher than erosivity of storm B. Now both the storms, they are falling on soil A, and of course they will be causing this storm will be causing more soil erosion than this storm B. But on the other hand, if the same storm B, it is causing erosion as X at soil A and erosion of Y at soil B, and X is greater than Y. So this means the same storm causing more erosion at soil A than at soil B. This means it is because of the difference in soil properties, what we call as erodibility. So this erodibility, which is you can call as susceptibility of soil towards the erosive agents, and erosive agent could be either rain or wind. So if the soil is more susceptible, its erodibility will be higher. If it is less susceptible, its erodibility low, and again it depends upon the type of soil or the soil properties. Now we will discuss about what are these soil properties which affect this soil erosion. The most important soil property affecting soil erosion is soil texture. Otherwise also soil texture is very important property from which we can judge so many things about the soil. So the first most important is soil texture. And you know that we have sand, silt and clay particles. Now erosion, I told you that this erosion basically is a two phase, but many times we say that it is a three phase phenomenon. One is detachment and another is transport, and third one is sedimentation. But erosion is said to have taken place when these two processes take place. If there is detachment and no transport of particles, we will say erosion is not there. On the other hand, if there is no detachment, then there will not be any soil particles to be transported. On the other hand, the transporting agent may be so strong, but non availability of soil particles to be carried by the run of water will not be there. Now these sand particles, these are the biggest particles. So these are too heavy to be carried out, to be transported by run of water, because these are the biggest particles. On the other hand, the clay particles, these clay particles make strong aggregates. If the soil contains higher amount of clay particles, that soil will have strong aggregates, stable aggregates, and detachment will be difficult. So, here in case of sand particles, transportation was difficult. In case of clay particles, the detachment of aggregates will be difficult. So, only the silt particles, these are most susceptible to soil erosion, because unlike clay particles, the silt particles do not adhere to each other, they do not result in formation of stable aggregates. At the same time, they are smaller particles than sand particles to be easily carried out by the runoff water. So, this is one effect of soil texture. Second is soil texture determines the infiltration rate of soil, because sandy soils we have already studied in our soil physics lecture. Sandy soils, they have higher infiltration rate, and clay soils, they have lower infiltration rate. Though other factors are also there, that how water moves in sandy soil, how it moves in clay soil, but of course, the final infiltration rate of sandy soils is always higher than that of clay soils. So, higher infiltration rate means lesser runoff, and lesser runoff means lesser soil erosion, because less water will be available to be carried away as runoff water. So, in clay soils, infiltration rate is low, so runoff will be higher, and higher runoff means higher soil erosion. So, this is how the indirectly the soil texture, it affects soil erosion through the infiltration rate of soils. Then after this, the sandy soils, as I said, are less swelling or shrinking type of soils as compared to clay soils. So, clay soils, because of their swelling and shrinking properties, because when these soils become wet, they swell, when they dry they shrink. So, because of this swelling and shrinking characteristics, these soils easily break down. Aggregates are easily broken down. So, that means detachment becomes easy when soil frequently swells or shrinks. It becomes, at the same time, now this is in here, as far as the effect of on transportation or detachment is concerned, clay reduces the erodibility of soil. But if you talk of swelling and shrinking properties of the, because all the clay soils are not swelling type or shrinking type, there are, it depends on the mineralogy of the clay. We have expanding type of minerals, like 2:1 type of minerals. So, soil having more amount of expanding type of minerals, they get easily broken down. So, that, but of course, it is the effect of the presence of the amount of soil particles present in the soil. After this, the second factor is soil organic matter. soil organic matter. You know, the soil organic matter, it has binding properties and binds the sand, silt and clay particles to form an aggregate. So, of course, higher the soil organic carbon, higher soil organic matter means stable aggregates, and stable aggregates means difficult detachment, and this means lesser erosion. So, a soil with higher amount of soil organic carbon will be less erodible than the soil having lower amount of soil organic carbon. So, this is very simple. Then after this we have third factor, that is aggregation. You know, aggregation means these are basically called secondary particles, and these are formed by binding of primary particles like sand, silt and clay. And this aggregation, basically it has two effects. One is the aggregate's size and stability. So, two things are very important. Bigger the aggregate, means lesser or difficult detachment. Generally, the aggregates are bigger in fine textured soils where clay plays an important role in binding the soil particles together. So, the bigger aggregates means higher clay content or higher organic carbon and less difficult detachment, and of course, this decreases soil erosion. So, this is second thing is, if the aggregates are bigger, the soil surface will be rougher. In fact, I generally ask this question to the students that you have two fields which are freshly plowed. One, how will you differentiate that which field is lighter in texture, sandy in texture, which field is clay in texture, without touching the soil, just having a look at the two fields? Can you tell me that which soil is sandy soil and which field is of clay or fine textured soil? So, the answer is, the rougher the surface, more will be the amount of fine textured particles or clay particles or silt particles. So, generally the clay soils are more rougher, and why these are rougher? Because of the bigger aggregates. So, these are rough surface, and if the surface is rough and runoff water moves over the rougher surface, on the other hand the runoff water moves over a smooth surface, in two cases the runoff velocity will be higher on the soil with a smooth surface. So, when the surface is rough, then velocity of runoff will be low, and low velocity means there will be more residence time for the runoff to stay on the surface of the soil. More the residence time, more will be infiltration. So, velocity this, infiltration rate will be higher. So, runoff will be less and soil erosion will be less. This is simple principle. So, now the big size, aggregate size has two effects. One is that because it is bigger, difficult to be detached, and it creates a rougher surface. So, that means when the surface of the soil is rough, the residence time of the water moving over the surface of the soil will be higher. Higher the residence time means higher infiltration rate, and higher infiltration rate means lower runoff and ultimately lower soil erosion. This is the effect of aggregate size. Then effect of aggregate stability. Simply stable the aggregate, difficult to be detached. So, stability of aggregates decreases, detachment of particles, and when there is less detachment, it means lesser soil erosion. So, this is how the aggregate size and aggregate stability, they affect the soil erosion. Then the next ultimately we say that this also determines aggregate stability, the crusting of soil. Now, crusting basically this is you can discuss it under soil texture also. Crusting is the formation of breakdown of aggregates into primary particles, then those primary particles they seal the surface of soil, and because of the pressure of the falling raindrops, they compact surface. So, a thin compact layer is formed at the surface of the soil, which we call as soil crust. Its bulk density is higher as compared to bulk density of the lower layer. So, sometimes if you have sown the crop and immediately after sowing there is rainfall, a sort of crust will be formed and the germination will not be possible. Now, this crusting, this is which soils will be more prone to crusting? Medium and coarse textured soils. So, here medium and coarse textured soils are more prone to crusting. Now, once the crusting is there, infiltration rate will decrease, because you have a fine layer, compact layer, it will hinder the infiltration rate. So, because of this, infiltration rate decreases, and then what will happen to runoff? Runoff increases, and this increases soil erosion. So, see the effect of crusting. Now, this crusting as I said, it is because of the medium and coarse texture soils. So, this is the effect of soil texture. When we talk of aggregation, the if you have stronger aggregates, could be because of dominance of clay particles, could be because of higher soil organic matter, then again aggregates will be stable, and when you have stable aggregates, the crusting will be less. So, I think you can discuss it under this. This is sort of overlapping, because even the aggregation, as I said, aggregate stability also depends upon the amount of clay particles, soil organic matter. But then yes, you may have different size aggregates. So, that is why aggregate size and stability are both important as far as soil erosion is concerned. Then comes next factor, that is soil strength. Sorry. For me, it is bit difficult to erase this board, electronic board, as compared to the traditional board, blackboard. So, I always love recording or teaching on blackboard, but here I have to use this because this room is very soundproof. Anyhow, so coming back, The third factor is fourth rather should be what we call as soil strength. So, when we say soil strength, it is basically, it has three parameters. One is bulk density. Second is penetration resistance. Penetration resistance of the soil, and third is of course shear strength. Now, first of all, bulk density. Now, bulk density, you know, it is mass per unit volume of the soil solids, dry soil. So, higher the bulk density, then that means the soil is tightly packed, and the total porosity, of course, that depends upon. So, here it is higher bulk density means compact soil. Now, what will be the effect of compact soil then? If the soil is compact, so we can we can say rather, not assume, that infiltration rate could be less, and lesser infiltration rate means higher runoff, and higher runoff means more soil erosion. So, this is how the bulk density affects, because it is compact. So, upon compaction the macro porosity decreases, and this macro porosity basically is responsible for transmission of water. So, if transmission of water is slow because of lower level of macro porosity, why lower level? Because of the compact soil. So, this is how bulk density affects. Then penetration resistance, soil penetration resistance. This is again similar to bulk density. The only thing is it is resistance of the soil to penetration, and it mainly depends upon in relation to, or better I should say, compaction in relation to soil moisture, because bulk density is mass per unit volume of the dry soil. So, there is no question of moisture. So, this is independent of moisture, but here in the same bulk density with two different moisture contents, the soil penetration resistance will be different. The soil having higher moisture content, penetration resistance will be lower. The soil with lower moisture content, penetration resistance would be higher. So, I am going to write this soils with similar bulk density, this is very important, may have different penetration resistance. Why? Because of differential soil moisture content. So, this is how the soil penetration resistance affects. Then coming to the third, that is shear strength. Now, the soil is basically a particulate matter. It is not a solid matter. It is not a solid. It is particulate matter. Soil is formed of particles, and these particles, when this soil is subject to some type of force, shear strength, soil being particulate matter, particulate material. So, when we apply some force, the particles roll over each other. So, these particles roll or slip over each other under the influence of some force. Now, that force could be the moving water, it could be the wind, it could be even when you plow the soil, you are basically shearing the soil. When you are plow the soil, you are not breaking down aggregates like we break with a hammer. We are not even if you hammer the soil, maybe the aggregate may get deformed, it may not break, or it may not break at the point where you have hammered it. So, the question is, because why it is so? Because it is a particulate material. So, when you apply some force, these particles roll or slip over each other, and then they get fractured or detach. So, here this detachment is this is called the shear strength. And again, this shear strength, it's the function of the type of the size of the particles present in it. So, a soil which resists the shearing force, its shearing strength will be higher. So, shear strength will be higher when soil resists the applied force. So, soil having higher shear strength, it will be less erodible, and generally this type of phenomenon happens like stream bank erosion, or even during the landslides, because landslide is also a form of erosion. So, when water moves, so with the force of the water, the particles they slip over each other and then the whole mass comes down. Similarly, when the water moves in a stream, it remains eroding the particles at the size, and once the particles they get fractured, the whole mass falls into the stream. So, this is the best example for shear strength affecting the erodibility of the soil. After this, then we will come, these were some of the mechanical properties, I should say structural properties, mechanical properties. Now, coming to the hydrological properties. Before that, I will have to rub this okay. Hydrological properties. So, we can say that this is second group of properties, hydrological properties. Now, in hydrological properties, the most important is the soil water retention. Some soils they retain more moisture than others. So, the soils which resist the effect of this moving effect of runoff water which is moving through the soil, or you can say fluid drag. The resistance of soil to fluid drag. When we say fluid, it means it could be liquid or it could be air also, or gas, better call as gas. So, we give a common name to liquid or gas as fluid. So, when fluid drag is there, then it depends upon, this resistance depends upon the initial moisture content, initial or antecedent moisture content, antecedent soil moisture. And again, this antecedent soil moisture is a function of soil porosity, I mean size of the pores, whether the soil is dominant in macropores or in micropores. So, that determines now if the soil is initially drier, so initially drier soil, it will be more prone to erosion. Sorry, it will be, I should say it's less prone to erosion. Now, why it will be less prone to erosion? Because when the soil is dry, we have basically the adhesive forces, cohesive forces. Because the soil particles, these basically the cohesive forces are the force of attraction between two similar particles. So, if it is a dry soil, the soil particles will be strongly attracting each other. So, here in this case, this will be less prone to erosion, it will be bit difficult to erode such soils. But on the other hand, if it is initially wetted soil, initially wet soil, then could be easily broken down. Because now the water molecules, they enter in between the two soil particles, force of adhesion decreases, force of cohesion decreases. So, another force, that is force of adhesion, comes in between, soil becomes unstable, broken down because it becomes unstable. So, if your soil is initially more wet or moist, it is easy for the raindrops to break such soil aggregates. On the other hand, if it is a dry soil, it is bit difficult to break the aggregates till the dry soil becomes moist. Then coming to the soil water transmission. So, this was retention. Now, the next will be transmission properties of the, but of course, these are under hydrological properties. So, instead of retention, now we will have soil water transmission. Now, soil water transmission, when we say, so it is, one is infiltration rate again. And just now we discussed the infiltration rate, it is a function of soil texture. And we also noted that higher the infiltration rate, lower will be runoff, lesser will be soil erosion, and vice versa. Second is the permeability. Now, permeability is a function of hydraulic conductivity. Now, what happens that once the soil enters into the soil, because infiltration is the just surface phenomenon, it is just entry of water into the soil. Once the water enters into the soil, then it starts moving within the profile. It may go down, it may move horizontally. So, whatever water moves down into the profile, we call it as deep drainage. Whatever water moves horizontally, we call this as seepage. Now, the question is how, what will determine whether water moves horizontally or it will move in x direction, y direction, z direction. That depends. If you remember in my soil water movement lecture, that Darcy's law says that this flux of water, and you know flux, it is volume of water per unit area per unit time. It is a product of hydraulic conductivity times hydraulic gradient. Now, hydraulic gradient is nothing but the energy level due to water at point A, energy level due to water at point B, the difference of the two divided by length distance between the two, that gives us hydraulic gradient. Higher the hydraulic gradient, higher will be the water content. So, I will not be going into detail of that. Second is hydraulic conductivity. This also determines the flux of water, because ultimately the flux of water is both the product of hydraulic conductivity and hydraulic gradient. Now, here hydraulic conductivity, if I say K, it is a function of permeability, we denote it as small p, and fluidity. Now, permeability, this is completely a property of the soil. It depends upon the properties of soil, purely properties of soil, like you have macroporosity, microporosity. More macropores, higher will be permeability. Lesser macropores, lesser will be the permeability. Then this fluidity depends upon it depends upon the properties of the water, whether the water moving through it is viscous. If it is viscous, its velocity will decrease. Now, the water which is moving, if this is laden with silt particles, its movement within the profile could be decreased. If it is pure water moving down the profile, its velocity could be higher than the viscous. So, it depends upon the viscosity of the fluid, then this temperature of the fluid. Temperature again determines the viscosity of the fluid. But we are concerned here with permeability, which is purely a property of the soil. So, this size of the pore, this again depends upon the texture, organic matter content, which properties we have already discussed. So, when we say soil water transmission, for infiltration as well as transmission of water within the profile, both are very important. Then this soil water transmission, we are talking of these things assuming that the profile is uniform. Now, supposing your profile is layered, it has 2 or 3 layers. This is sandy layer, this is clay layer. Now, water, when it will enter into this, infiltration rate will be higher. But once water reaches the boundary between sandy and clay layer, now the clay layer is basically the restricting layer. Now, the movement of water, flux of water will depend upon the velocity of water in this restricting layer. This is very important. So, even if you are seeing that soil is sandy, water is moving down, but after some time the water starts accumulating at the surface, and this soil gets easily eroded, because detachment is very easy in sandy particles than in clay. But again, because water is not moving down, it stagnates. Once it stagnates, then it becomes runoff, then the detached particles can be easily carried away. So, here in this case soil erosion will be higher. On the other hand, if it is other way around, say if it is clay soil at the top and sandy soil at the lower layer. Now, water, its infiltration rate initially will be lower. Once it enters over here, then the water will move down very immediately. It will go down, and maybe there is this infiltration, because infiltration may not be affected, it is a surface phenomenon. But again the restricting layer is clay layer. So, again this clay layer will determine the erosion, but again clay has its own effect, it makes the aggregate stronger, its infiltration rate is lower. So, those factors could be more important. Then this erosion may decrease, it may increase or decrease depending upon the dominance of the process, which process is dominating, which effect of clay, whether it has made the aggregate stable, erosion will be less. If it swell shrink, it has expanding type of minerals, then swell shrink, then erodibility could be higher even if it is a clay soil. So, this is how the things move. Third group of properties are the rheological properties. Sorry. So, here rheological. Basically, rheology, you can say rheology is a science that describes the behavior of soil particle, soil water system. So, it defines behavior of soil water system under the influence of applied force, and it depends upon the consistency of the soil. So, this basically determines soil consistency. Soil consistency, then basically rheology, consistency is based on the concept of rheology. So, this is behavior of soil to applied forces under different moisture contents. Now, you see your soil is completely dry, the aggregate, it is very strong because only cohesive forces are dominating. Then you add some moisture, some water in it. Now, water enters into, as I said earlier, so water enters in between the soil particles. Now, two type of forces are acting. One is force of cohesion was already there, now force of adhesion starts dominating. So, the clod is moist, if you apply some force, it may crumble depending upon how much clay content is there. Similarly, then add more moisture, then you can mold it into different shapes. We have already studied, you can go back to my lecture on soil consistence, and there you can find out the details. So, the question is how soil behaves at different moisture contents. So, initially when rain falls, there is soil erosion process begins. Initially, as said, soil is dry, the force of cohesion is dominating, particles are very cohesive, bound to each other, then it depends upon the amount of clay, amount of organic matter that determines. So, as the soil gets wetter, its behavior changes, and ultimately when it becomes a completely sort of flowing liquid, sort of we say that it flows like a molten butter, water content increases to such an extent, then the again only force that acts is water, then even force of cohesion disappears. So, now it is cohesive forces are because of the presence of water in the soil water system, and then soil starts flowing, and this happens, soil flows like semi-liquid, or better, molten butter. This is, I think, the highest amount of water present in soil, and this leads to then landsliding. That is why landsliding, or even you can say mass movement. So, whole mass of soil comes down because now the consistency of the soil is such that soil starts flowing easily. So, it no longer gets bound. So, this is how this rheological properties they affect. This was third group. Now, coming to the fourth and last group, that is chemical and mineralogical properties of the soil which affect soil erosion, or you can say which affect this erodibility of the soil or capability of soil to get eroded. So, chemical, sorry, it's yeah, chemical and mineralogical properties of the soil which affect soil erosion. So, here in chemical properties, it's basically soil, you know, it has it's a colloidal complex. Either this, if you remember in my initial lectures, this is soil colloid or soil particle. Then this soil particle, it could be charged, then there could be net negative, net positive charge. So, ultimately the net positive or net negative charge will determine, you know, the force with which, you know, water molecules there, because water molecule being bipolar in nature, they get attracted towards this. Or instead of this soil particle, it could be soil organic matter. That's also part of, you know, the colloidal complex. So, then you have different type of, you know, calcium, magnesium, then sodium, potassium, different type of, you know, this cations which are attracted, even anions which are attracted towards the soil particle or soil organic matter, depending upon the net negative charge of the soil colloid system. So, here the exchangeable cations, that calcium, the bivalent, because these are bivalent cations. So, bivalent cations like calcium and magnesium, these keep the soil stable and soil erosion is less. On the other hand, the monovalent cations, like sodium, potassium, these make the soil unstable, and the soils or the complexes, colloidal complexes which are dominant in you know, monovalent cations, they can be easily eroded. And at the same time, if sodium is dominant, sodium dominant soils, because this leads to, you know, dispersion plus lower infiltration rate. In this case, because the soil gets dispersed due to presence of more amount of sodium, the zeta potential increases, then soil disperses. So, it can be easily broken down. Even if it is a clay soil, it is dispersed in nature, and once it disperses into primary particles, the soil surface, soil pores, they get sealed, and because of the dispersion, the downward movement of water or infiltration rate reduces. So, this is basically the characteristic of the sodic soils. In sodic soil, generally whether it is rain water or irrigation water, the water does not stagnate at the surface of the, it stagnates at the surface of the soil, and it is always muddy water. So, stagnant water, if it is muddy, even after few hours of stagnation, you can easily judge that this soil is basically sodic soil, which is dispersed. Particles are there in the water, they do not settle down because of the dispersion. So, this is how the exchangeable cations, they affect the erodibility or soil erosion ultimately. Then another effect of this chemicals is heat of wetting. Now, this heat of wetting, in fact, this is when you wet the soil, then the amount of heat which is released, it depends again on amount and nature of clay. So, this depends upon amount and nature of clay, and this heat which is so released, this increases, this is an important effect on soil structure and ease of particle detachment. So, this heat of wetting, it eases particle detachment. So, again this heat of wetting is basically the indirect impact on soil texture. You can discuss this point in soil texture as well. Then is soil profile characteristics. The characteristics of the soil profile, these also affect the erodibility of the soil or soil erosion. One effect I have already discussed, that is when it is layered soil. So, profile, you can call it as next group, fourth or fifth, profile characteristics. One we have already discussed, that is the profile could be layered, and as I said earlier, the layer, the most restricting layer, that will determine the extent of erosion or runoff taking place, number one. Number two is the vegetative growth, I should say the root biomass. If the vegetation is growing on such soil, and because of vegetation, the root biomass in the profile is well developed, such root biomass keeps the soil particles bound together. So, this root biomass helps in reducing soil erosion. Detachment could be difficult as compared to the bare soil. So, here root biomass, or you can say vegetated soil, vegetated versus bare soil. So, this affects the profile, because profile in a vegetated soil may have sufficient biomass, root biomass, which protects the soil from erosion. And then rate and type of water flow, then again rate and type of water flow. So, this depends upon the arrangement of layers. Whether if it is overlying layer is sand, clay, or it could be aggregated at the top, compact at the bottom, we have already discussed. So, this is how the soil profile characteristics layering it affects. Now, supposing you have a sand at the top and infiltration rate after some time decreases, then the sand, this layer may immediately get eroded. So, this is how the profile characteristics they affect soil properties, ultimately soil erosion. So, these were some of the properties of the soil which we discussed, which affect. Next, we will learn about the erodibility indices. Thank you very much.